All right, well, hello everyone, good morning. Thanks for organizing this fantastic workshop. Topics and attendees are great, the location is fantastic. The plan for today is, so I'm at Georgia Tech. I've been supported by the Department of Energy for the last 7+ years, so this has been great. Hopefully this continues. So the outline for today is to go pretty heavy on the introduction, keeping to the spirit of being a tutorial. Try to motivate a little bit why we study quantum magnetism, my research approach, which is the research approach of many people, and how inelastic neutron scattering and modeling can go together in solving problems. And then perhaps I'll give a few examples, and we can probably call this greatest hits from 2012, 2025. So most of you have probably heard about these topics. I hope that I can play the song again, but maybe with a few additions compared to what you may have heard before. And then I did not have time to do a great conclusion, so you will see. So anyway, let's get going. Let's get started. So in quantum magnetism, we are trying to understand the physics of magnetic insulators. And so, of course, this contains a lot of quantum physics, and perhaps it's important for application. But at the fundamental level, we have a very complicated high-energy physics coming from the electronic Hamiltonian that merges the crystallography of the materials we are looking at, the quantum chemistry where the orbitals are, the electronic correlations. So there's a lot of electronic phenomena at high energy that are complicated and diverse. And in some sense, in magnetism, in quantum magnetism, what emerges at low energy is a single or few energy scales related to quantum spin exchange. And that gives us the Heisenberg model. And so, at the simplest level, the magnetic model that emerges from all of this is just spins living on the lattice that interacts through quantum exchange. I lost the pointer, but OK, that's good. And so, we've learned yesterday that, this Heisenberg model from 1928 probably did not come from the Heisenberg paper of 1928. But anyway, my research has been on studying this kind of Hamiltonian in some details. And recently, it's kind of fluctuating with fashion. The type of magnetic Hamiltonians people write for materials have been evolving and changing. And in some kind of generalized sense, you can write the magnetic Hamiltonian as an anisotropic or a matrix that couples two spins on two different sites. The range of interactions may be more than just nearest neighbor, so they can be all sorts of competing interactions in space. And then, importantly, especially in nowadays, you have anisotropies that come from the local Hilbert space. You can have higher order exchange terms. You can have disorder. So this magnetic Hamiltonian that emerges from electronic systems in their insulating limit is quite rich and quite complicated. And so the goal for today is to explain how we study these materials and what kind of physics we can understand from them. Okay? And really, in some sense, that's the goal. What is the kind of correlated physics that emerges from these magnetic Hamiltonians? And so you can imagine many different states of matter. You can imagine long-range ordered systems. You can imagine systems that have multipolar order. And then you can imagine systems that have entanglement, be it local, as in quantum paramagnet dimer systems, or in the most extreme case, quantum spin liquids, where entanglement lives at certain length scales. And really, that's the point, understanding the correlated physics of these magnetic insulators. And why do we care? There is a fundamental pursuit here. Maybe we can realize new states of matter. Perhaps, as we will hear in the next talk, perhaps we can stabilize new forms of quantum field theory. That's kind of a physics way of thinking about it. Have exotic quasiparticles, maybe discover that systems have long-range entanglement and things like this. Perhaps we also care because we simply want to understand low-energy excitations. They are important, after all, probably for technology and applications. And perhaps because I'm in the US and everything has to be AI these days, perhaps our ultimate mission is to produce models that we can fit to the AI, and then the AI will tell us which next material to study. Of course, in practice, this is not how this works, but still, I think at the end of the day, we produce models, and models are useful, and they allow us to understand the next step. So even if AI is not involved, the outcome being models is actually good. So how do we do that research? there's many different models, but recently, maybe in the last 20 years, people have really focused on this kind of feedback loop between the discovery of new materials, the growth of new materials, the spectroscopy of these materials, and the coupling with theory. So that's really something, when I was a postdoc at the IQM at Johns Hopkins, this was really the mode of operation is to really have that feedback loop. And I think a lot of groups are operating under that kind of model. And my strengths, I would say, is really uncoupling the neutron spectroscopy, or my group strengths, and the theoretical modeling. But we should never forget that samples are essential, and discovering new materials is actually the limiting factor in some sense. And so a great emphasis should be on that and having them clean and properly characterized, et cetera, et cetera. And although my focus is on neutrons, there are many other spectroscopies that are complementary, and in some cases, or maybe often superior. You can think about electron spin resonance, all sorts of optics, as Rolando discussed yesterday, and emerging perhaps two-dimensional spectroscopies and other techniques that may bring great insights on these systems. So neutrons are less and less operating in isolation, and you see more and more studies where everything is working together, and I think this is the sign that the field is evolving into a very mature and reliable state in some sense. Okay, so I will show some data that is not neutrons today. So stay shockingly. Okay, and so another point is that it's often useful to extract models to understand what materials do, and often a semi-classical regime is something you can use to do that. And so here I give you a simple phase diagram of it's a kind of aspirational phase diagram of a magnet where you can control the temperature, you can control the magnetic field, and there are several regimes in which you can obtain a semi-classical state. So that would be, for instance, at high field where you saturate the spins. That would be at high temperature where you have a Curie-Weiss regime, but you can extend it to finite momentum. And sometimes ordered states are good states to be semi-classical, sometimes they are not. So you will see in my talk a lot of instances where we go to these limits to extract a model, and then we go to a more complicated regime to try to understand the physics. And I want to say that it's not the only approach you can use, and in fact, emerging is the fact that you can do quantum calculations, high-fidelity quantum calculations in a parametric fashion. So here's an example from work from Sasha's and Steve White's group, where you can use DMRG to actually probe the phase diagram of a material and kind of try to refine the physics. And Sasha and Steve have been pushing this to great extent. So you don't always need a semi-classical state to understand the models, but at least for us, that's what we tend to do. Okay. And so now the main technique is inelastic neutron scattering. So that's what I've been using since my PhD. So just quickly to remind you the strengths of the technique. So you illuminate a sample with a beam of neutrons. The neutrons carry a spin 1/2, so they can interact with the system through a dipole-dipole interaction. So you can transfer angular momentum to the sample. And of course, you transfer momentum and energy, and this momentum and energy are comparable to the energy scales of condensed matter. And the beauty of the technique is really that what you measure in the detector, the cross-section, is directly proportional to the dynamical structure factor, which is the Fourier transform of spin-spin correlations. And this, this is an exact cross-section. There's nothing else, at least in most limits. And so that really makes this technique quantitative and really useful for model extraction and for finding the truth in these materials. Okay, so I'll show a few little details here that I think might be important to to see what the frontiers are. And really, what has been driving the physics recently is progress in instrumentation. So historically, neutron scattering is done with what is called a triple-axis spectrometer, the greatest Canadian invention. After maple syrup, perhaps. And so the triple-axis spectrometer allows you to visit momentum energy space and to measure the cross-section at different points. And this is not a very efficient technique because you're doing this visiting four-dimensional space in a point-by-point fashion. So here is an example from a paper by Christian Rueg's group in a ladder system where there is only one direction of momentum space, so triple axis might actually be the way to do this kind of experiments. But as soon as you're looking at samples that have multiple dimensions involved, this triple axis machine become really slow at probing momentum energy space. And what has really changed the game is the emergence and the understanding of how to do experiments on machines we call time-of-flight spectrometers. So now instead of having one detector, you have millions of pixels that detect the neutrons. So this is a massively parallelized detection of where the neutrons are going. And then, if you rotate the sample and you use the time of flight of the neutrons to understand energy transfer, you really, with one single parameter that you scan, you're essentially doing a four-dimensional momentum energy space map. So these are examples here on the left of diffuse scattering, so structural disorder in a material, and on the right, these are some spin waves in momentum energy space that we can directly get from these measurements. Okay, so this has really allowed wide surveys of momentum energy space, and it's a great discovery machine in that sense because you can find signal you are not expecting, and that is often how the field proceeds in some sense. So a few additional tricks about neutron scattering, given that it's a tutorial. So one great thing about the fact that the cross-section is quantitative is that you can do a lot of things without any model. You can do a model-free interpretation of your scattering. And one great example is the sum rule. So if you sum the dynamical structure factor for all space and all momentum, what you should find is NSS plus 1, so you're measuring the expectation value of the spins on a given side. And so this is already doing a non-trivial quantum measurement. You notice that it's SS plus 1, not S squared. And so you are already trying to, when you do this sum rule measurement, you are sensing the full quantum mechanics of the system. So recently, people have repacked this kind of concept in what is called entanglement witnesses, which at the end of the day is just how the sum rule is distributed is momentum space. And so it's really a measurement of the quantum nature of the system, but the sum rule already captures this. And there are a few fun stuff you can do. If you have a Heisenberg system, so if the spins, if your Hamiltonian does not have anisotropy, you can extract quantities from neutron scattering that allow you to directly measure correlations between spins and energies of bonds without any modeling involved. So here's the example on the left of what we call the instantaneous structure factor. You integrate over all energies, and that gives you something that is proportional to the spin-spin correlations weighted by Fourier sums. And another thing you can do is calculate the first moment. So instead of integrating over energy, you integrate over energy times energy. And so that allows you to extract not the spin correlation, but the spin correlation weighted by the exchange interaction on the given bond. So this, if you have a Heisenberg system, which is not always the case, especially nowadays, we have a lot of anisotropic systems, but you can actually directly measure spin correlations and directly measure bond energies without any modeling, which again comes from the fact that the cross-section is in absolute units, and you can do this in a fully quantitative fashion. So really, really powerful technique in that sense. And another part of the physics of neutron scattering that is useful and interesting. I'm sorry that the laser is not. Do I have it? No. Okay. If I release it, I lose it, but that's okay. So one important part of the cross section is this dipole factor here. I'm good now. Ah. Can I get it blue? I'm joking. I'm joking. Yeah. Okay, good. So in the cross section, so we don't directly measure the structure factor. We measure the projection of the structure factor perpendicular to Q, and that type of that element in the cross section is very useful. So here's an example from Joe Pattison where you can show that this projection perpendicular to Q, if you have a system that is anisotropic in spin space, you can actually, through this polarization factor, you can understand directly the type of anisotropy that you have without any true modeling. You can just sense, how spin space is related to momentum space, and therefore you can know what type of spin anisotropy exists in your system. So again, it's more than just Heisenberg systems. You also have in the cross-section something very useful to understand anisotropy in spin space. And all right. So there will be some nice breaks like this. Okay, and another thing that you can do is you see here in the cross-section, you have the different components, alpha, beta of the structure factor. And with polarized neutrons, you can actually extract any component you want of that structure factor. So this is an example here from my PhD where we look at a multiferric material that has a spin cycloid like this. We prepare it in a single chirality by applying a magnetic field, electric field. And what you can see is that you have a Bragg peak that lives only in one channel, y minus x. So you're essentially sensing the chirality in the system. And so we cannot really do this in the inelastic fashion right now. It's very difficult to do in inelastic fashion. But future instruments will be tuned and optimized so that we measure all the 9 components or 6 components that are identical of that tensor in momentum energy space. So really, polarization analysis will allow you to extract these quantities. So, you know, for the theorists in the room, which is most of the room, we care about the different components in alpha beta space. And we have emerging instrumentation to go after these correlation functions. Okay, so one last thing about neutron scattering that I want to mention, and that's actually the vexing part of the problem in some sense, is the energy resolution. So the typical energy resolution of a neutron spectrometer, the way we can think about it is delta E over E. So E or EI or EF. EI and EF is the wavelengths we use to probe the material. So imagine this as the top of the bandwidth of your system. And your resolution is of the order of 2 to 5%, which if you compare to optics is absolute rubbish. I mean, what you've shown yesterday, for instance, with your, optical spectroscopy where you can resolve essentially megahertz, our resolution is absolute crap compared to what you can do with lasers and optics. The typical lowest energies we can probe with neutrons, we come with EI equals 3 MeV. So it means our energy resolution is of the order of 60 to 150 micro eV. So this is actually quite poor energy resolution. So there are ways to, people have mentioned this, I want to just emphasize that point again. There are ways to go around this that do not utilize the energy of the neutron as a way to do energy. You use the spin of the neutrons to resolve energy. So this is done in spin echo techniques. And the challenge here is that what you want is a good energy resolution at finite energy transfer. So there is a machine in Munich called TRISP that does this. So essentially the way this works is you prepare a wave packet of neutrons. They may have slightly different velocities. You make them evolve in a field. And so, like in a typical NMR experiment, in some sense, they're going to dephase. Then the sample scatters them. So, it will flip the spins. So this kind of stuff will be inverted. And then if there is some energy transfer, some of the spins will go faster, some of the spins will go slower. And then in the second part of the spectrometer, you can recombine the signal. And then you're going to have and you can change the field integral in that part of the spectrometer. And then you're going to have an echo at a particular field integral matching. And the resolution you can get in this type of experiment is of the order of 0.1 to 10 micro eV. So Sasha and the late Bjorn Falk, on looking at liquid helium-4, did such experiment here, looking at the line shape of the roton, and you see that you can get very good energy resolution and understand the line widths of your excitations. But the vexing part here is that there is a huge gap in resolution between this kind of 60 micro eV and maybe 10 micro eV, and this is where a lot of the problems actually lie. In other words, this resolution is too good for our crappy samples, and this resolution is too bad for our pristine samples, so to speak. So really, this resolution gap I consider a huge problem, and again, future instrumentation should really be geared at closing that gap, because I think there's a lot of physics that is awaiting in that particular regime. Okay, so I'll skip this. There's new emerging type of spectrometers that are called prismatic analyzers, and so we're really trying to do better, but it's not quite there yet. It's a fantastic machine at the PSI called CAMEA, where you essentially use the Prism ID to resolve, to essentially do super resolution on your experiment. And that allows you to be very efficient in constructing these QE maps. But the resolution in this type of machine is still of the order of 3% of delta E over E. So resolution remains the challenge. Okay? Good. So now let me talk about modeling. So there's, as I said, semi-classical approaches are usually very useful. So we have spin wave theory. I think Jeff will talk about this more. The good part of spin wave theory is that it's based on quasiparticles, so you can interpret what you're doing. You can understand, physically what's going on. The bad or the, perhaps sometimes the problematic part is that you need the right spin configuration to do it, and sometimes it's not that obvious. And doing it at finite temperature is complicated. And what is emerging, although it's been there for a long time, but people are using more and more, is Landau-Lifshitz dynamics or classical dynamics, which works completely differently. It's good because you can do finite temperature modeling. It contains classical nonlinearities, as I will show maybe in the end. This contained a lot of physics, perhaps not fully understood yet. But the bad part of this is that it's the stochastic technique by nature, and the thermal bath is classical, and so that at low temperature gives you wrong answers for, say, specific heat and things like this. And I just want to mention that these techniques have been generalized to include multipolar degrees of freedom, and I'm involved in the SUNY collaboration, which is trying to coding all of this in a unified framework. But at the same time, what has been quite exciting recently is that full quantum approaches have been used to model directly neutron scattering. So here, this is an example from Andreas Loschli's group where they use matrix product states to directly calculate the dynamical structure factor of the triangular lattice antiferromagnet with, I think, a ribbon side of 4 or 6. So it's really becoming 2D DMRG, and so this can be very useful as well. Of course, they don't have the ability to really scan parameters so quickly, and so it's still emerging as a technique. Other trends that are exciting is, I will show a little bit what we now call truncated Hilbert space, ED. So essentially, instead of doing exact diagonalization in your spin system, you can take your effective magnetic Hamiltonian and do some kind of exact diagonalization of it. So that can be very useful to detect Magnon bond states. We're working on techniques that allows us to do spin wave theory, linear spin wave theory, but for very large systems which may have disorder. So there's a paper we recently published on what is called KPM. It's a way to do spin wave theory without diagonalizing the matrix, which allows you to be super fast and do very large systems. It's quite exciting to see the developments in parton decomposition and going beyond mean field. So Batista's group and we heard Johannes yesterday. So many different techniques go in that direction. So really the modeling is really, everything is coming together and the instrumentation is getting better. So it's really a fantastic, exciting time to work. And now we can revisit some of the greatest hits in this. Just for the students, I think, we don't live in a world where people do things independently anymore. Experimentalists, especially with things like SUNY, will venture into theory. And we've seen yesterday that theorists like Sasha are venturing into experiments. And so, this is fantastic time to kind of cross and do a little bit of both. Of course, we are very aware that some great damage can be done by experimentalists not knowing what they're doing with the theory. So we also have to be careful about this. Okay, anyway, so let's do some of the greatest hits and show you a few of the stuff that, just kind of like showing how neutron scattering evolves in some sense across a decade and through my work. So first I'll start with the, I have to talk about copper sulfate, but probably give a bit more details in this particular talk than usual. So this copper sulfate material is one of many materials that realize weakly coupled spin 1/2 chains. And what's cool about that material is that the energy scale is extremely small. So the interaction between the spins along the chains is of the order of 1/4 of a millivolt. So that's the chains here. And they are weakly coupled with each other. And that exchange here is at least 1 order of magnitude smaller. So it's a good one-dimensional system. But because the energy scale is so small, it almost does not order. It orders, in fact, at 92 millikelvin. But you can use a very modest magnetic field and you can saturate the spins. So it means, remember in the cartoon I gave in the beginning where you can go to high temperature, you can go to finite field, you can really explore the different regime of this system. The vexing part about it is that there is another copper here that lives in the middle of the crystal that is weakly, almost decoupled from the rest, and that complicates a little bit the physics, especially at intermediate field. But let me show you the first thing we can do with this is to essentially go in the saturated phase and measure the magnetic excitations. So because there are 2 coppers in the unit cell, one type of copper in the chain, one type of copper almost decoupled, you see two modes, so copper 2 and copper 1. And here, this is an experiment where we do triple axis, so we're really measuring every point in momentum energy space. So every dot here is where a measurement was conducted, and then we interpolate the data in this color map here. And so what you see here is essentially dispersing magnons. And the beauty of the triple axis experiment is that if you look at single Q and single line shape, you have actually pretty good statistics, and you can really see your peaks and that are resolution limited here. And as I change the momentum transfer, you see that the peak of copper 1 is moving while the peak of copper 2 is not moving. And so this is the dispersing part of the chain spins. Okay? And the typical way of analyzing this is you fit the data, you put some points through a graph like this, energy momentum, and then you try to fit this with the results, say, of linear spin wave theory, which is exactly what is going on here. And so you can extract the spin coming from the chain. So you see we are at 5 Tesla, so it's above the saturation field, so there is a Zeeman gap. And then you see the bandwidth of the system, which is here 2J, so you have a direct measurement of the exchange. And then these modes here are flat, and so you see an energy corresponding to the G factor of the second spin. And because the symmetry is so low in this material, the G tensor of the two spins of the two copper side is different. So that's why if you look here carefully, they don't, at the gamma point, you see that the two modes do not exactly overlap because the two coppers have different G factor. So that's all good, and I'm sure you all seen graphs like this. The point I want to make here is that you can go beyond just fitting the position of the peaks. You can also fit the intensity, okay? And here again, the cross-section being quantitative, if you think about this, the cross-section that you measure is going to be some kind of stuff that depends on the instrument and the material, and then your dynamical structure factor. And here, because you're measuring always per Q and you've saturated the system, you essentially only measure SYY. And in a saturated ferromagnet, SYY is just S divided by 2 Dirac delta function of the dispersion. Okay? And so here, when I put the data in the instrument units in some sense, I see that this number here, whatever it is, 22, corresponds to S/2 per copper. So I have an absolute normalization of the intensity of the neutron scattering process. And that can be very useful to understand different types of physics. Okay? So keep that in mind. Now what I'm showing next is releasing the magnetic field. So now we are above TNEL, and of course the spectrum changes drastically. This is the celebrated Spinon continuum. And if you look at a particular position in Q here, oops, so at that Q, again, triple axis measurements, measuring all these dots here, and you have this signal that of course is not resolution limited. You see the extended tail of the signal that finishes at some particular energy. And so this continuum corresponds to the creation of pairs of spinons. This is very well understood. And because you have better Ansat and now all sorts of matrix product state techniques to calculate this in DMRG here to calculate this effectively. But again, what I want to emphasize is that again the cross section here is is twice SYY. So why is there a factor 2? Because now we are isotropic, so we have twice more correlations to probe. And then we still have the same prefactor in the cross section as we had before, but now we know it from 5 Tesla. Okay? And so because we know it from 5 Tesla, we can compare the theory and the data in absolute units. And when I do this in this material, the model and the experimental intensity are in agreement with a scale factor of 0.99. I have an error bar of 8% on this. But it means we can do the measurement in quantitative absolute units. And here in this problem, there's no surprise. We understand everything about the spin 1/2 chain. But imagine materials where you don't know where the moment is. So for instance, the metallic system, you don't know how much moment is living on a particular side. So normalizing your data and using this kind of techniques can be really useful to understand the magnetism. So I think that's really the point of this. And of course, a beautiful example of the emergence of spin-on continuum, in zero field while you had spin waves at 5 Tesla. Okay? Good. So at 0 Tesla, the second copper is in the elastic line, is buried in the elastic line. So for the full story, of course, what you want to do is you want to measure intermediate fields. So you probably know in intermediate fields, the continuum splits in different components, and there's all sorts of exotic excitations, beta strings, and all sorts of stuff. But in this material, as you go to intermediate field, you have this huge paramagnetic line that is sweeping across the spectrum. And that makes it very complicated to analyze. Yeah, just for the full story here, attentive reader may ask, why is the copper 2 more intense than the copper 1? That should not be the case. Each copper carries spin s, spin 1/2. And that's because there is some multiple scattering in the material because of some residual water. So, I'm burying a lot of details under the rug here. So, absolute normalization is great, but you have to, sometimes you suffer a little bit. So anyway, good. So let's go to, so if there's no more questions about this, then I'll talk about square lattice problems for a little bit. And so the next thing you might want to do after having done the spin 1/2 chain is look at spin 1/2 square lattice. So there's a well-known material called CFTD. So this is some kind of metal organic framework here. So you see the square lattice. It orders at a temperature of 16 Kelvin in a Néel state. And the moments, which is important for this discussion, the moments point in the A. So the square lattice is the AB plane, and the moments point in the A, along the A direction here. And here you see now, this is a time of flight measurement. So now we measure the full momentum energy space in the 2D square lattice. And so you see the spin waves emerging out of the Néel ordering point at pi, and then going to high energy. And between pi/2, pi/2, and pi0 is what we call the zone boundary. And so you see the nicely dispersing spin waves in this system. So I will always get confused between CFTD and CFDT, which is one of the French unions. And when I was a teenager, my mom was in CFDT, and every dinner was about the union and so on and so forth. So if you hear me saying CFDT instead of CFTD, this is, I cannot get out of that. So, yeah. So anyway, so this is, that's that material. And so one intriguing aspect of this material is that if you do simple calculation, you would expect that the pi/2 point and the pi0 point have the same energy and also the same line shape. But this is already apparent in this experiment that this is not the case. So one of the way we can, the reason I'm talking about this is one of the way we can solve and advance on this problem is to use this polarization analysis technique to understand what is going on at high energy here and compare these 2 points to understand is it something that is happening in spin space that is leading to this kind of discrepancy. And so here is an experiment where we do exactly this. So the structure factor here contains, in this system, 3 components. So XX, YY, and ZZ. And so the way I will discuss this is that there's going to be components that are transverse to the ordered moment, and one component that is longitudinal with respect to the ordered moment. The neutron scattering cross-section contains something perpendicular Q. So it means you only measure spin correlations in spin flip perpendicular to Q. So if I essentially put Q along the ordered moment, along the A-axis, I can measure X, XX, and SYY. These are the transverse modes. And if I put Q along the ordered moment, I will measure the longitudinal fluctuations. Q perpendicular to the ordered moment, I will measure the longitudinal fluctuations and one transverse fluctuations. And with polarization analysis, we can separate each component independently. Okay? So this is the result here. So you see, when we put everything together, pi/2, single Magnon mode seems to be well behaved. Pi0 seems to have some kind of line shape here. So that's the intriguing part that is seen in the time of flight. You see also the intensity is much weaker. And then we can decompose this problem into the transverse part and the longitudinal part. And you see that this continuum lives both in the transverse part and in the longitudinal part, which is the intriguing part of the physics. And if you put the two of them together, you see that essentially this extra continuum that lives at pi0 seems to originate from some kind of isotropic continuum in spin space. So that's kind of the power of the technique to go and analyze a detail in your dispersion in the structure factor and understand, how does it behave in spin space. So when I was a grad student, I tried to use 1/s² spin wave theory to analyze that data and understand, is this essentially here we have a collinear magnet. So the next best thing you can do after calculating your 2 Magnon continuum, which is in the longitudinal channel, is to calculate the 3 Magnon continuum. And if you do that calculation, you find that the 3-magnon sideband in 1/s² spin wave theory is essentially vanishingly small and very, very diffused. So we cannot really, at the time, we could not really explain this in terms of Magnons. But there's been some development since, in particular, the group of Gotz-Uhrig posted this very nice paper that essentially reproduces the line shape that is observed. And the part that I was missing as a student is what is actually important is that it's at pi/2 that there is this peak in the longitudinal channel. So there is almost a quasi-particle peak in the 2-magnon continuum. And that actually tells you that something is happening between the Magnons. And what is happening is that in the non-perturbative sense, the Magnons are attracted to each other. And that leads to, so here is a pi/2 point. The green line is what you would expect from non-interacting Magnons. And when you do this non-perturbative calculation, you see that there is a peak emerging in the continuum. And so really, these line shapes are a signature of how the Magnons interact at a high energy. And here it seems to be effectively a mutually attracting Magnons in the system. So yeah, there's more coming on this. We're actually doing field work. But I just want to mention a bit of history. This is the 15 years anniversary of my first paper, which is with Sasha, which is my master's thesis. And the goal here was to calculate what happens to the square lattice when you apply magnetic field. And so because you have a non-collinear structure, you're going to have cubic vertices. And so the Magnons should be interacting very strongly and with cubic anharmonicities. And in fact, a lot of the thing I've been trying to do since on the square lattice was trying to track this and to find the effect that above a certain field, roughly 75% of saturation field, you should have very strong Magnon decays. So if you want to do this on CFTD, you cannot do this because the field scale is too large. You would need 2,000 Tesla or something. So you need to move to another material or other materials. And so here, one such material is called CAPCC. It has very, again, a small energy of interaction and small saturation. So now you can do this kind of measurements. And so this is still not published, and I'll explain why in a minute. When you apply a magnetic field on the square lattice, you have two types of fluctuations now. You have fluctuations that are uniform in the magnetic field. It's essentially a double Q structure, Q equals 0 and Q equals pi. So you're going to have modes related to these two things. And where Magnon decays, so for instance, at this 3.2 Tesla here, this is where we expect the Magnons to decay. This is also where these two modes actually cross. So it's been very difficult to extract the Magnon lifetime from these measurements because there's a crossing between two modes. And we've been struggling with understanding the resolution function of the spectrometer for a long time. So, you know, my goal as a student was to measure Magnon decay in square lattice, and to date, we have not published this. But in trying to do something completely different, then we saw the most beautiful decay where I never would have expected, and that's what I want to do next. So you learn something, you want to apply it to the obvious thing, and sometimes it's in the non-obvious things where you detect what you're looking for.
How do you know the models are Heisenberg for CFTD and that other one?
Yeah, so that's a good question. So for CFTD, the symmetry is actually low. You see all this, you see there's actually this DM interaction. So there's some quite nice ESR measurements from a long time ago that put some limits on the DM. You know, I think at the level of 1%. But, you know, I'm still thinking, hey, what if this, you know, maybe this could play some role.
My memory is that CFTD also had easy plane. They reach
Weakly easy plane, yeah.
Yeah.
So yeah.
Okay.
I mean, there could be.
Modeling?
We've not re-grind this through modern times. So that might be worth it, yeah.
So, but then these two Magnon attraction, the peak that develop, could I think of that as a bound state of two Magnons?
So it's not a bound state in the sense that it does not, it lives inside the continuum. Okay, so it's not, you know, the bound state usually goes below the continuum. Here it's some quasi-bound state, or I don't know what you want to call it. It's some enhanced density of states for two Magnons. A resonance might be a way to talk about it. Yeah, that's good. Yeah.
And it show up near the single Magnon energy?
Say that again.
Does it, the bound state, does it show up near the twice of the Magnon energy?
So here you see, oops. So this is just above the 1 Magnon energy, okay? So you see, this is the 1 Magnon peak here at 15 MeV, and this quasi-resonance here lives just above it, okay? So the 2 Magnon continuum lives from the 1 Magnon energy to the 2 Magnon energy. But at the bottom of that continuum leaves this resonance, okay? So it's not a bound state. It's not, it's not living on its own, but it's an enhanced density of spectral weight, okay? Good. So yeah, okay. Let's continue if you don't mind. So then you do something else. I started my position as assistant professor, and then then we did something completely different, and then the Magnon decay came again. So that's the story of FEA2, real quick. And so now, a completely different thing you can imagine studying is systems that are not spin 1/2, but spin 1. And here, that model of that FEA2 sample has been known since the 1970s, studied actually in astonishing details by several French groups at LLB and in Japan. So a lot was known about the system. And if you simplify it to the extreme, it's essentially a spin 1 ferromagnetic easy axis chain. Of course, the chain is embedded in a 3D system, so it orders. And so the 2 ingredients that are necessary to understand the physics, first is that you have spin 1. So if you want to describe the fluctuation of the spin 1, you need to involve not only dipolar fluctuations, but also quadrupolar fluctuations, because you can go from spin SZ plus 1 to spin SZ minus 1. So there are many different ways you can do this. One way is to write a coherent state of SU3 to describe the local physics. And then the Hamiltonian is essentially a single ion anisotropy that dominates the system and some exchange. Okay, so that's the physics of the system. And then you can ask yourself, what are the excitations in such system? So compared to the spin 1/2 case, you're going to have new types of excitations. So of course, you're going to have, at low energy, a single spin flip that's give you, SZ from +1 to 0. So that's a 1 Magnon. And then you can create different types of multi-Magnon states. So you can create 2 Magnons far away from each other. You can create 2 Magnons on neighboring sites. So we're going to call this a 2 Magnon exchange bond state. And what is special about the spin 1 system is that with this type of anisotropy is that you can also create what people call the single ion bond state, which is a double spin flip on a single site. Okay? So all these excitations can live in principle in the system. And if you want to, you can think about this excitation as quadrupolar because you act with the spin minus operator twice on the same site. Essentially all of this was known. Our new insight was to realize that in this material, in a good fashion for the times, there is off-diagonal exchange, so Kitaev-like exchange in this material. And that actually allows these excitations to hybridize, and through some magic, we can see this in the neutron scattering. So again, these are the ingredients in this material. It's much more complicated in practice, but we have a spin 1 system, so it has 2 types of local excitations, 1 Magnon and single ion bond state. In principle, you should not see the single ion bond state. It's delta is equal 2, so spectroscopy does not allow you to see that excitation. You have single ion anisotropy that controls the energy of the single ion bond state. You have a regular exchange that controls the dispersion of the 1 Magnon. And the new ingredient, you have some off-diagonal terms that will hybridize these excitations. And by some magic, the 1 Magnon and the single ion bond state, because D is 10 times J, and by some magic of quantum chemistry, these 2 excitations overlap in energy. And because they hybridize, you can see this. So this is the result here of an experiment where we measure this FEA2 material. It has a more complicated magnetic structure than just the chains. It's actually some 2 spins up, 2 spin down type structure. But that explains why there are so many bands. But in essence, what you see is 2 bands of excitations in the neutron response. And you see that one band is almost flat, except when it seems to be crossing with this 1 Magnon dispersion where it hybridizes. And here, there is a huge, there is a gap between this excitation band that looks like some hybridization gap. And this is exactly what is going on. These off-diagonal terms actually hybridize your different flavors of excitations. And we can model this with spin wave theory generalized to dipolar and multipolar spins, and just looking at the dipolar sector, now you see that we can quantitatively match the data and understand what is going on. Okay, so here the real ingredient is that you have a more complex local Hilbert space, and so you have different types of local fluctuations. And by magic, they overlap and they hybridize. And so we can see not only the dipolar sector, but we can see the influence of the quadrupolar sector on the dipolar sector in this magnet. So then, with the group of Pete Armitage, in fact, we were trying to do 2D spectroscopy on that material. Did not work out. And then, we got regular spectroscopy in the end. And so here, so this is the Q equals 0 response of terahertz spectroscopy, so terahertz magnetic field. And you see that, at the 0 field, you have this single ion bond state, you have your Magnon bands, but when you apply the field, you see that suddenly there seems to be a lot of complicated spectra here with a lot of lines seemingly coming from high energy. And you would notice that the slope of these excitations is very high. So excitation with high slope in this type of experiments means the G tensor is very large, and you can fit the data. And what you observe is, of course, some of the lines correspond to one Magnon. Some of the lines correspond to the 2 Magnon bond state that I already discussed. And then this line seems to have 4 times the 1 Magnon G factor, and this one's even 6 times. So this is evidence of 4 Magnon and 6 Magnon bond states in the system. And it's pretty natural to construct these excitations here. So your 1 Magnon, again, is a single spin flip. The 2 Magnon bond state, you flip twice on the same site. And then once you've done that, you can start to create exchange bond states where you flip 2 spins twice on neighboring sites, and then here you can do it 6 times essentially. So there's a plethora of bond states that can exist in the system. And essentially, it's almost a flat band system. So there is strong potential energy because D is 10 times J. There is a weak dispersion, and so you can pile up all your bond states all the way to, in fact, 8 Magnons in this compound. Okay? And so here, the way you can understand this and model this is to use this truncated Hilbert space technique. So you take your effective Hamiltonian. You can keep certain states. So here, the 2 Zongs, they keep all the way to 4 Magnon excitations. And you see that they can, not all the features, because there's also 6 Magnons, but they can reasonably calculate the spectrum of the system using that technique. So we, again, even in a complicated setup with up to 4 Magnon bond states, we can have a almost quantitative understanding of the spectrum. Should watch our time. Yes. And then to close up on the decay ID, then motivated by this, we went back to do neutron scattering in magnetic fields. So now not only looking at Q equals 0, but looking at finite momentum. And so the spectra here that we see in 0 Tesla starts to be very complicated. You see different modes splitting, et cetera, and very rich and complicated. And here, perhaps where we least expected in the spin 1 system that seemingly has a large anisotropy, you see that some of the spin wave dispersion here seems to be completely vanishing and becoming very broad. And that's actually a striking example of Magnon decay. Where at least that's not what we were looking for, and I was not expecting it in that particular material. But just to convince you that indeed there is some anomalous line shape, this is the spectrum at that particular Q vector in 1 Tesla. So you see our resolution limited peaks. And then when we go to 4 Tesla, where decays are allowed, you see that the width of the excitation is dramatically enhanced. And so that's the evidence for Magnon decay. So then, where is this coming from? So again, this is an example where anisotropic exchange gives you something you did not, at least I did not expect. So in this example, this is this J plus minus term. So this is one particular parameterization. So what this allows is terms that have S plus. So you can have a Magnon that emits a single ion bond state and continue its way, or you can have a single ion bond state that decays into 2 single Magnons. So these decays are because essentially the quantum number is not preserved anymore. You can have this kind of decays that are allowed, and if the kinematic conditions are fulfilled, then decay can happen. And so Shang-Shun Zhang calculated all of this. It's relatively complicated because you have many different bands and sublattices and so on. But there's some regions of strong decay that are predicted here, and this is in the data also where we find the decay. So this is very clear that this is what is going on in this system. Okay? So then there's even more interesting physics or maybe details, depending on your point of view. There's also some regimes where we predict, or this truncated Hilbert space technique predicts some decay, but they are not seen in the experiment. And the physics here is that when a single magnon emits single ion bond states, these two single ion bond states can recombine into a 4-magnon bond state. And that actually leads to an avoided decay in some particular regime in field. So all these quasiparticles really form, that's the title of zoo. There's really a zoo of these quasiparticles that interact with each other. And you know, it's first of all, it's remarkable that this shows up in material like this, and that we can, you know, to some extent, completely understand it with modern techniques that are semi-classical, or I mean, this is not semi-classical, but at least that are reasonably fast to deploy. Okay. So yeah, I mean, so the message here is that you know, looking for spin 1/2 systems and looking for decays, and then we go to easy axis spin 1 system, and that's where we find the decay. You know, I'm almost out of time, so I just want to very briefly mention that all this being said, continuous excitations does not always mean fractionalization and decay. There are many other phenomena that can take place that gives you a continuum or gives you what looks like a decay. I just want to just zap through them. In some systems, you have strong disorder. So here's an example of this triangular lattice magnet. At 0 Tesla, beautiful continuous spectrum of excitation. We apply the magnetic field. The continuum persists. This is not good. That cannot happen if you have a clean system, unless you have something very special. So magnetic excitations can be broad because of exchange disorder. So don't believe everything you see. You know, ask to see the high field dispersion. There's other reasons why you may have continuum excitation. Here's an example of a highly frustrated system, spin 3/2 parachlor antiferromagnet, magnesium chromite. You can go to very low temperature, and because it's so frustrated, you are still in the paramagnetic regime at 10% of the Curie-Weiss constant, or less than that, 5% of the Curie-Weiss constant. And here you see the spectrum of excitation of this system. It is structured, but it is also continuous. Okay, and here, this is because of frustration. Magnetic excitations are broad because the spin ride a slowly fluctuating background. There is essentially a slowly fluctuating paramagnet, and your spin waves are, you know, fast harmonic oscillations around this, and that gives you a continuum. So again, that's another type of continuum that has nothing to do with decay and fractionalization. And perhaps the latest thing we've done with this Landau-Lifshitz dynamics is absolutely, you should never do that, is we try to model the spin 1/2 chain at finite temperature with Landau-Lifshitz dynamics, with classical dynamics. And to our surprise in some sense, you can see that, so here's an example of these classical simulations, corrected in some ways, but very simple ways. And here's the example of quantum Monte Carlo from Wolfram Brennig's group. And this classical dynamic simulation essentially reproduces you know, this continuum of excitations all the way to perhaps T over J equals 1/2. Okay? So in the nonlinear classical dynamics of a magnet, you have some physics that mimics continua, and that can really make it, you know, look like you have fractional excitations. So again, you know, if something is measured at finite temperature, you know, and if it's continuous, it can be a finite temperature effect. So, you know, continuum of excitation does not mean fractionalization. You need to check you don't have disorder. You need to check you at low temperature. And what is the last one? The intermediate one. And you need to check that you're not highly frustrated. And I would say 90% of the case says that's what is actually going on. With this, I don't have a conclusion besides what Sasha told me, quoting it's a quote from Sasha quoting someone else. And the conclusion is, so Magnons are stable, right? So at the end of the day, if you don't care about Magnon decay, you will never care about Magnon decay. But in this room, we are believers. And so, you know, I hope to convince that this is an interesting topic. And so with this, thank you very much for having me and for your attention.